Hi everyone, so this is lesson 4 on types of chemical reactions. This is probably going to be the most difficult lesson in this section. You're going to have to classify types of reactions and write balanced equations for each type, so you have to know how to write balanced equations. You're going to use something called a reactivity series to determine if a single displacement reaction happens when we get to those. Use solubility rules to determine if double displacement reaction happens, and predict the products of different types of reactions. So the last learning goal here is the most difficult one, and if you can do this, then you are probably able to do the other three, because this one involves doing the other three altogether. Types of reactions. So these are the ones you're going to have to know: synthesis, decomposition, single displacement, double displacement, and combustion. So we're going to go over all 5. Okay, number 1, synthesis reactions. So this is when you take two reactants and you combine them, and out of those two you get a single product, meaning a single substance. So when you balance the equation, there could be a 2 or maybe a 3 in front of what you have on this side, but you will only be producing one thing. You're not going to have a plus sign over here, just one thing by itself. So something plus something else gives you just one thing. If you see that, that's a synthesis. So an example would be when you add hydrogen to oxygen in this balanced equation. So you can see here we've got 2 oxygens. And 2 oxygens on this side, right? Remember, 2H2O means that you have 2 H2O molecules. Each one has an oxygen, so there are 2. So 2 oxygens, 4 hydrogens, 4 hydrogens. So this is a balanced equation. We can see this is a synthesis reaction because you add 2 things together and you only get one substance on the right, only water, nothing else. So this is actually a really useful reaction. It's used to power rockets. Turns out if you combine these things together, although in rockets usually those would be liquid, but when you combine those two together, you can generate a lot of energy. And so this is actually the rocket launch of the Mars Orbiter mission launched by India a little bit earlier in this decade. Decomposition. If you know synthesis, decomposition shouldn't be too hard. It's just almost like the opposite. So you have one thing, one substance, and it breaks apart to form multiple substances. So the general form is you have something, and then it breaks into 2 things. So an example would be something that we've already seen. So if you have hydrogen peroxide, that can break down into water and oxygen. It might need something called a catalyst to do that if it's going to happen quickly. This reaction does actually happen very slowly, which is why if you buy hydrogen peroxide from Walmart or pharmacy or something, you'll find it has an expiry date. But this reaction can be made to happen much more quickly if you have a catalyst. So for example, peroxisomes have the catalyst that will do this, or you can add something in there. You can add manganese dioxide or potassium iodide, if I remember, will do this if you've ever seen the elephant's toothpaste reaction. All that's happening is you have hydrogen peroxide in there, which is a liquid. They put a little bit of soap in there so it can trap the air bubbles. Then you put in the catalyst that's actually not part of the reaction, but triggers this process. And so once this starts breaking down and forming oxygen gas, the bubbles trap the gas, and so you get this weird foamy stuff. Okay, but this reaction anyways is just one large thing which breaks apart into 2 things. There's a useful video on this. If you want to see this in a little bit more detail, explained a little bit more, you can watch this video. But basically what I'm going to expect is just you can look at a reaction and tell me, is it synthesis or is it decomposition, and can you balance the equation? Single displacement. Okay, so now we're starting to get a little bit more complicated. If you look this up online, you'll sometimes see them called single replacement reactions, but this is the same thing. So what you have happening is you have an element out here by itself, and you have some kind of compound. So the element will react with the compound, and it will move in and displace part of this compound, which will then go on to be by itself. And so they often explain this with this kind of analogy. So imagine we have a couple here, and then you have this person over here who is much, much more attractive, and so he is able to displace poor Frank over here, and we have a new couple. So this analogy, it's kind of goofy, but the reason I think that we use this analogy is because it actually explains something else that you have to know about this process. And that's that single displacement reactions aren't always going to happen. in order for the reaction to happen, A must be more reactive than B. So Joe over here can displace for Frank. Frank, unfortunately, just doesn't have the right stuff. He can't go back and displace Joe. So what does that have to do with this reaction? Well, if A is more reactive than B, the reaction can take place. But if B is more reactive than A, the reaction cannot. So in other words, this thing that's out here by itself has to be more reactive than the thing on the inside in order to take its place and kick it out. If it is less reactive, then the reaction actually won't happen. You'll have no reaction. So this here is what we call a reactivity series. And you can see what's more reactive and less reactive here. So you up on the top of this list, you have your alkali metals, potassium and sodium. We have this one here in order to be a little bit more gender equal, where we have this girl, I guess, is going to get kicked out here because lithium is very high up on this list. We actually don't have lithium on this list, but if we did, it would be right there underneath sodium. And we typically don't use those two because they can be quite dangerous to react. So lithium would be in there. So if you have something higher on the list as your A and something lower on your list as your B as part of BC, then the reaction can happen. So potassium, for example, could react with gold chloride. So K could react with AuCl2. It would kick out the gold. But copper would not be able to kick out, say, aluminum. So if you reacted copper with aluminum nitrate, copper would not be able to kick it out. You would just write no reaction. No reaction occurs. Okay, so some examples. So here we have zinc reacting with copper 2 chloride. So you'll notice then as well with these reactions, typically the element that's by itself is solid. And the element that is combined is aqueous. These reactions tend to happen in water. So this is dissolved in water, and then you can put this lump of metal in there if you were to do this in an experiment. And then you would see the reaction take place. Okay, so you'll form zinc chloride and copper. Right. You could do... you could try and do the reverse reaction. So you could try to add copper to zinc chloride, but no reaction will take place. And we know that because copper is lower on the list than zinc. So if I was trying to see about this reaction, will this reaction happen, I would see, aha, zinc's by itself. What's it reacting with? It's reacting with copper. So I want to see, is zinc higher than copper on this list? Yes, it is. Zinc is there, copper's there. So the reaction can proceed. Reverse, right? Okay, I've got copper, and it's trying to kick out zinc. So is copper more reactive than zinc? Here's copper, there's zinc. No, copper is actually below zinc, so no reaction takes place. And you can just write no reaction if no reaction takes place. Double displacement reactions. So this is where you have two compounds reacting. Okay, and this is a good way you can start to think about in identifying these reactions, right? When you see two compounds, you know this is double displacement. And what happens is the positive ions switch places so that each has a new partner. So if my positive ions are A and C, A is originally paired with B. It's now going to pair up with D. And C was originally paired up with D. It's now going to pair up with B. So switch partners. Okay? And often when this happens, typically your two compounds on the left are soluble in water, so they're dissolved in water. But one of the compounds on the right is not soluble in water, so it forms a precipitate, which means it forms a solid that comes out of solution and you can actually see it. So when I like to do this, when I do this reaction in class, I like to show this example. So you've got a aqueous substance there and an aqueous substance here, these two clear substances. So remember, aqueous means dissolved in water. So this one here, I'm not sure which of the two it is because they're both clear. My guess from the color is that this is your lead nitrate. So it's lead nitrate, which is a white powder, but it's dissolved in water, so you don't see it. And down here you would have your potassium iodide, which is also a white powder, which becomes clear when you dissolve it in water. So once you mix the two substances, you get a reaction that takes place, and it's actually this reaction here. So potassium iodide with lead nitrate, lead 2 nitrate, I should say, and that produces lead 2 nitrate, and lead 2 iodide and potassium nitrate. So to see if you understand your state symbols, this yellow color that you see here, what substance is that? Right, it's a product, but you have two products. So which one is the yellow color? Can you figure it out? All right, well, the answer is going to be, it's the lead 2 iodide. And we know that because it says S here for solid. So that's the part that's coming out of solution and forming the precipitate. The potassium nitrate is actually still in there, and you can't actually see it. Although, if you were to evaporate the water, you would be able to maybe obtain some of it. Last one, combustion reaction. So there are many different types of combustion reactions. We're going to focus on the combustion of hydrocarbons, which means things that are made up of carbon and hydrogen. So things like CH4 or C2H6. So we're always going to have some number here and some number there. Combustion can get more complicated. You can have combustion of things that have oxygen in them as well. So CXHYOZ if you like. Maybe have nitrogen in them. You can have combustion of metals. But we're only going to do, for the purposes of this class, this type of reaction only. So you react something with oxygen, a hydrocarbon, and you provide heat. So essentially what you're doing is you're burning this compound here. And you have an arrow that goes over, and when you burn it, you produce carbon dioxide, water, and energy. So this is what happens when you have a fire. So I don't know. I actually should have looked it up. I don't actually know how the Olympic torch actually works. I don't know what fuel is being burned there, but presumably some kind of fuel. It could be, I don't think it's gasoline, but gasoline is one of these. Gasoline would be octane, which is, if I remember, that would be C8H. So that'd be C8H18 would be octane. Or it could be some kind of oil or some kind of gas, but in any case, it's going to have a C and an H in it and maybe something else. And then as long as there's oxygen in the environment, and you have you have a heat there, then you can burn this. And as long as there's oxygen and fuel still there, it will continue to burn. It will continue to produce CO2 and H2O. Sometimes, though, if there's not enough oxygen present, instead of forming CO2, you might create pure oxygen, so you might produce CO or just C. So if you produce just C or carbon, you'll see soot, you'll see black sort of stuff starting to appear in this area. If you've ever heated a beaker on sort of a low flame, you might have seen black sort of soot accumulate on the bottom of the beaker. That would be just carbon. Or if you also don't provide enough oxygen, you could produce CO, which is carbon monoxide. And yes, that is that carbon monoxide, that nasty stuff that can kill you. So that's why when you're burning something, you want to make sure that you have an open environment. If any carbon monoxide is produced, it can escape and not cause you to suffocate. Okay, so let's get on to some examples. Classify and balance each type of reaction. So we have a full reaction here, right? We have reactants and we have products. So can you tell me what type of reaction this is? And can you balance the equation? All right, so let's move over to Word so I can do that. Here we are. Okay, classify and balance. So let's balance this first. Okay, we've got one calcium, that's good. We've got two oxygens, that's good. We've got two hydrogens and two hydrogens. Good, so this one's actually already balanced, so I don't have to do anything other than classify it. What type of reaction is this? Well, you can see that we have one substance, and it breaks apart into multiple substances. So this is going to be decomposition. This example here, okay, so we got one calcium and one calcium. We've got two nitrates and two nitrates. Or if I prefer, I could say I have two nitrogens and two nitrogens. 2 times 3, so I have 6 oxygens and 6 oxygens, so that's all good. One iron. This one's already balanced. Okay, it's my lucky day. What kind of reaction is this? Well, I have one element and a compound. So you should immediately know, if you see just an element and a compound, that this is going to be a single displacement. Okay. I have here Na2, Okay, this one's going to need to actually be balanced. I have two NAs on this side, but only one on that side. So I'm going to put a 2 there. I have one BA, I have one BA, I have one S, I have one S, I have one, no, I have two N's, right, because I put a 2 there. I have two NaNO3s, so I've got 2 of those. I've got 2 N's there. Oxygens, let's total those up. I've got 4 oxygens from the sodium sulfate, and I've got 6 oxygens here from my barium nitrate. So 4 and 6 gives me 10 oxygens in total. On this side, I have 6 oxygens from my sodium nitrate, and I have 4 oxygens from my barium sulfate. So that would mean that I have 10 on this side. So now this is fine. This has been balanced. Okay, this one should be easy, right? We've got one compound here and another compound. You're adding 2 compounds together, so you know what type this is going to be. And you can see that the partners have switched. So sodium used to be with sulfate, but now it's with nitrate. Barium used to be with nitrate, but now it's with sulfate. So this has been, both things have been displaced. So this is double displacement. As a bonus question, if you were to carry out this reaction with these 2 reactants being aqueous, and you produce your product, which one of the products would you see? So the answer to that one is going to be barium sulfate, because it's a solid. So this one would still be dissolved in solution. You wouldn't see it. Last example. Okay, so we've got iron and we've got oxygen. I'm definitely going to have to balance this because you can see here I've got 2 irons on that side and only 1 on this side. So I'm going to put a 2 there. And I need to balance my oxygen. So I've got 3 on this side and I've got 2 on that side. So, okay, this is a little bit challenging, right? I could put a number here, but that's not going to fix the problem because I have a 3 and a 2. I could put a fraction there, but if I want to use whole numbers, this is going to be a little bit tricky. So here's how you can approach something like this. You can use kind of like the common multiple or common sort of denominator approach. So I have a 2 here and I have a 3 there. So if you were trying to find a common denominator, for example, between 2 and 3, you could multiply those numbers together, right? So if I want to add 1/2 and 1/3, then my common denominator would be 2 times 3. It would be 6, right? So you can try to figure out how to get these both to be 6. Well, I could put a 3 there, and I could put a 2 there, right? So now I've got 6 oxygens on the right-hand side and 6 oxygens on the left. But the issue now is that I have 2 and I have Fe2O3. So each compound here has 2 irons, and I have 2 of them, so that's actually 4 irons. So I'd have to change that to a 4. Okay? And again, you're playing around with this, right? So if you put in numbers and then you find that you have to change them, that's no problem. You're not doing this in a systematic sort of way. You're kind of just figuring it out. So feel free, just if you're changing stuff all the time, that doesn't matter. If you're able to do it and you feel confident and you're getting the right answers, then you're doing fine. Okay. So we got to classify this one. So we're adding 2 things together to make just one thing. So this would be a synthesis reaction. Okay. So that's it for balance and classify. So we'll go back. And now we're going to get on to the hardest type of question that you will get in this topic, and probably the hardest type of question you will get in our whole chemistry unit, including days 3 and days 4. And that's this. I'm going to give you some equations, and I'm going to ask you to predict the product. So not only am I going to ask you to balance the equation and tell me what kind of reaction this is, but you actually got to fill in what goes in over here, which can be a bit tricky. And I'm going to give you one of these whenever I ask you this type of question. Hopefully you're already aware of why you might need one of these. But if not, we're going to see in these examples why this is here. Okay, back over. Predict the product, Mg plus O2. So let's figure out what kind of reaction this could be. So you'll notice there are no compounds in here. So that means it's not single or double displacement, because in both of those you have compounds, right? In single displacement you have an element and a compound. In double displacement, you have 2 compounds. So it's not either of those 2. We don't see any CXHY, so we're not going to do combustion of hydrocarbons, so it's not that. Decomposition would mean you have one thing and you're breaking it apart. So we have two things here, so it's not that. So there's only one thing this can be, right? This has to be a synthesis reaction. And you're adding these things together. So if you add magnesium and oxygen, well, there's only two things there. So you must make magnesium oxide, right? That's how you combine magnesium and oxygen. So how do we know what the formula for MgO is? Is it MgO, or are there like subscripts there, or what's going on? Well, remember, same as usual, you go to this thing, Mg has a charge of 2 plus, oxygen has a charge of 2 minus, they'll combine in a 1-to-1 ratio. So it is actually just MgO, so that's just it. So now we're going to balance this, so we're going to put a 2 there, so that we have 2 oxygens on the left and the right, and a 2 there to balance out the magnesium. Don't worry about a subscript there. It would actually be a solid if you do this. Actually, you may have seen this done in class. It's pretty cool. It gives you a very bright white light. You can't actually look directly at it or it will mess up your vision, but it works pretty well. Okay, next one. Na plus CuSO4. So we've got sodium plus copper 2 sulfate. So what could this be? Well, we have an element and we have a compound. So that already tells us what it is, right? An element and a compound. We have one type of reaction that looks like that. And that would be your single displacement. So sodium is going to try to displace copper. Is that possible? Well, that's why we need this list. So where's sodium? Sodium's near the top. Is higher than copper? Yes, copper is down there. So can sodium displace copper and get this reaction to take place? Since it's higher, yes it can. So we're going to get sodium is going to go with the sulfate. And sulfate, remember, has a charge of -2. So that 2 will go with the sodium. Sodium has a charge of +1, so the 1 will go with the sulfate, but we don't show the 1, so that's it. And then we get copper metal by itself. Okay, so if you like, this one will be aqueous, and this one will be solid. Okay, we gotta balance this. So we need 2 sodiums. So we're gonna have 2 sodiums over there. 2 sodiums, 1 copper, 1 copper, 1 sulfur, 1 sulfur, 4 oxygen, 4 oxygen. Great, we're good. So that's this reaction. Next up, copper 2 chloride and silver nitrate. Okay, 2 compounds. So again, we should know what this is right away. 2 compounds means what? It means double displacement. So both of these are going to switch partners. So remember, you actually don't need to access this chart if we're talking about double displacement. There is something else you have to do with double displacement that we're not going to do this year. It has to do with solubility. But if you take grade 11 chemistry, you're going to worry a bit more about that. Okay, so we know they're going to switch partners. So copper is no longer going to go with chloride. So which one does it go with? Does it go with Ag or does it go with NO3? Well, remember that these are ionic compounds. So positive is going to go with negative, right? You have a cation and an anion, a positive ion and a negative ion. So copper has to go with the thing over here that is negative. So Ag is positive, right? Ag is a metal, it's silver, has a +1 charge. And NO3 is a polyatomic, it's nitrate with a negative charge. So that tells you that copper's got to go with the NO3 because that's the thing that's negative. So we're going to get copper nitrate, or copper 2 nitrate, as we should say. And we're going to get silver chloride. Okay. So now that we've done our double displacement, let's balance this. We've got 2 chlorines on this side and only 1 over here, so I'm going to put a 2 there. I have 2 silvers on this side, but now only 1 over there, so I'm going to put a 2 there. And I think that should do it. We've got 1 copper, 2 chlorines, 2 silver, 2 silver, 6 oxygen, 2 nitrogen, 2 nitrogen. Yes, we're good. Okay, last but not least, our final example. We have gold plus potassium nitrate. So what kind of reaction will this be? So again, we've got an element by itself, and we've got a compound. So if this reaction takes place, it's going to be a single displacement reaction, right? The gold will replace the potassium, which will then get kicked out and exist by itself. But remember, we got to consult this to see if the reaction is going to take place. So gold would have to be higher up on the list than potassium if this reaction is going to happen. but we can see that gold's actually on the very bottom of this list and potassium's actually on the top. So potassium could kick out gold, but gold just can't kick out potassium. So we say that this is no reaction. And you can just write it like that. Okay, and this is one of the reasons why gold is so valuable, right? It's a nice and shiny metal, but it doesn't tarnish. It tends to stay shiny for a very, very long time. Sodium can be shiny. If you actually cut into a lump of sodium, you'll see it's shiny. It's not a nice yellowy kind of color, but it's shiny on the inside. But it tarnishes very quickly when it reacts with the air and it forms a less shiny material. But gold doesn't react. It's very unreactive, so it's going to be shiny for a very long time, which is why one of the reasons why I imagine that people like it and it's so valuable. Okay, so that's pretty much it. If we go back to our learning goals, can you classify the different types of reactions? So remember all 5 types. Can you tell me which one's which? I should have just said them. So synthesis, decomposition, single displacement, double displacement, and combustion. Can you use that reactivity series and tell me, will this single displacement reaction happen or will no reaction take place? Can you perform a double displacement reaction? I'm actually going to change this learning goal. I've made things a little bit harder with this one. So basically, can you perform a double displacement reaction? Can you tell me what's produced at the end of it? And can you predict the product of different types of reactions? So if you can do all those things, then you are good for this lesson. And you should be good for most of chemistry. There's one other thing you have to do after this that's hopefully a little bit easier for you. And then we're at the end. Okay, that's it. Thank you.